Hey, what's up YouTube? Thanks for joining me. We got a cool video here on basal ganglia, and we're going to talk about the functions. I made a figure here, basically putting, I think, what any professor might expect you to know about the basal ganglia, and I try to get it all into one figure so we can have one kind of study source we can refer to. So feel free to take a screenshot of this, and I'm going to explain the basics of how this diagram works. So first thing is, why basal ganglia? I mean, what's the point of it? Why is it important? Basal ganglia is sort of a place where the brain can store motor plans, and in addition to the cerebellum. So the cortex can consult the basal ganglia as to how to execute a motion in a smooth and fluid way in coordination with the cerebellum in order to execute that. So you see some diagrams with just the cortex projecting down into the spinal cord, and that's kind of just one side of the story where it seems as if the cortex is just executing motor plans, but in reality, the cortex is first consulting the basal ganglia in addition to the cerebellum, of course, before it executes those actions. Now, I like this figure I made because I've kind of color-coded it to make it super simple. And you may think this looks complicated, but if you remember just a few basic rules, I say 2 basic rules, it's going to be really easy to remember this layout. The first rule I'm going to say is that this lentiform nuclei, so this is the structure here, this sort of curved shaped nuclei, is going to have only GABAergic neurons. And since those are considered inhibitory, I've made those sort of a reddish orange color. So anything that you draw out of the lentiform nuclei, and by the way, they're lentiform because they're shaped like a lens, should be GABAergic. Now everything else should be glutaminergic, so I've designated those with green, except for, of course, the famous substantia nigra, which I think you get so hammered with Parkinson's disease, you should be able to remember that its neurons coming out of it are actually dopaminergic. So the lentiform nuclei, GABAergic, everything else glutaminergic except substantia nigra, which is dopaminergic. All right, with that basic layout, you can, for the most part, be able to draw these pathways. Now, there's considered to be 2 basic pathways. One is a direct pathway, and it's direct because there's no consultation of the subthalamic nuclei as in the indirect pathway. So the direct pathway is going to go straight from the lentiform nuclei to the thalamus, whereas the indirect pathway will go through the subthalamic nuclei first. Now notice the subthalamic nucleus, as I said, has a projection of glutaminergic fibers here. So let's just walk through the pathways one by one so we quickly can understand how the signals are flowing. So the cortex is going to send a glutaminergic signal to the putamen, which is this outside section of the lentiform nuclei. That's going to activate a GABAergic neuron, which is going to send a signal which is inhibitory onto an inhibitory GABAergic neuron. Now what happens when you inhibit an inhibitor is that this doesn't fire here. And so this neuron, which is glutaminergic, is free to fire and send a signal back to the cortex. So overall, the effect of the direct pathway is to stimulate firing back in the cortex. As you can see, I've noted that as a positive sign here. Now, the indirect pathway is, as I said, going through the subthalamic nuclei. Let's walk through that real quick. So a glutaminergic or a positive signal is sent down to the putamen again. Now this time, instead of having a cell body in the globus pallidus externis, as in the direct pathway, you see this is in the externis portion of the globus pallidus, we're going to have a cell body in the internis portion of the globus pallidus. So it sends this signal, activates this glutaminergic neuron, and again it inhibits an inhibitor, allowing a release of inhibition on this subthalamic nucleus. And then this fires a positive signal, allowing this glutaminergic neuron to fire, and then this is going to inhibit the thalamic nuclei here causing an inhibitory signal back to the cortex. So just remember that double glutaminergic or GABAergic signals is in effect going to be a kind of a positive, an indication of fire for the next neuron. That can kind of simplify it a bit. But what about these signals? What do they do here? So some people like to conceptualize this as, say, a flexor, and this is an extensor. So if you want to bend your arm, this would project onto neurons that need to flex, and this from the indirect pathway would project onto neurons that need to extend. Any motion, as you can imagine, involves a flexor and extensor, that is one muscle relaxing and one muscle contracting. Now the only other thing we have to discuss is, in terms of neurons, is the substantia nigra with its dopaminergic system. So this is where some detail is involved. There's two different receptors on these GABAergic neurons. One of them is a D1, and that's in the direct pathway, and the D2 receptors on the indirect pathway, GABAergic. Now, the effect of D2 is inhibitory, and the effect of D1 is stimulatory. So what happens is this signal is going to be the opposite of this signal, and in some way it's going to negate it. And so just here you can imagine that the overall effect back at the cortex of the indirect pathway is going to be the opposite of it, without considering these substantia nigra D2 interference. So you get the opposite sort of signal. Whereas on the direct pathway, when the dopaminergic neurons fire onto these D1 receptors, you see that there is a stimulatory effect, and that matches this cortical neuron, where you can see the overall effect in that sense would be that it increases that signal. So in some sense, it's going to, say, increase the activity of a flexor, and at the same time it's going to also increase the activity of the extensor. Now you may wonder, why would you want to increase the activity of an extensor? Don't you want to, say, if you're bending your arm, don't you want to have that inhibited? Well, if you don't have some sort of nuance to the system, you can imagine that the extensor, if over-inhibited, may cause the flexor to have more power than you may want, and you may overshoot your motion. So in this way, you can see that the substantia nigra is a system for fine-tuning the movements of these direct pathway and indirect pathway. Now this is sort of just the basics. If your professor has you naming all these fibrous systems, these axon systems, I'm going to go over the kind of nomenclature for that real quick. So fibers projecting from the cortex to the putamen can be called corticostriatal. So all of these things sort of have a prefix or a suffix that you just combine together for whatever relevant fibers that you want to name. So fibers from the cortex should be called cortico, fibers from the putamen should be called striatal. Now the fibers coming from this putamen region, remember we named those as striatal, so this system we should call pallidostriatal. So the prefix being pallido and the suffix being striatal. Again, this would be a pallidostriatal, and this would be a pallidosubthalamic, and so on and so forth with all these, as you can see, these prefixes and so on that I've put here. So say you want to name these fibers, what would you call these? So we're going from a thalamic to a cortico, so we say corticothalamic fibers would be these. So naming them is actually fairly simple, as long as you can remember that this is striatal, because the rest of the names are pretty much straightforward. Globus pallidus, pallido, nigro for this, and subthalamic, thalamic, and so on and so forth. I think that's all I got for you guys. Thanks for watching. If it helped, please like the video. Feel free to subscribe, and cheers. Have a great day studying, y'all.